In this part, we are going to look at what are the stress field around a screw dislocation. So as you know that dislocations are line defects, and you have already seen the bonds near the dislocation line are broken or stretched up. So there will be an elastic stress which is generated around the dislocation. Let's say here I'm taking a screw dislocation. So I have a bonds which are stretched around this dislocation line, and thus there exists an elastic stress field around this dislocation line. And here we are trying to find out what is that stress field around a screw dislocation. So here I have shown a screw dislocation, and you can see that this is a dislocation line, and the Burgess vector, let me mark it over here. So the Burgess vector is in this direction, which is parallel to a dislocation line. So to find out a stress field around a screw dislocation, what we do is we take this cylinder, which was perfect, and as we have discussed it earlier, that we put a Volterra cut and we shear this dislocation in a such, or we shear this cylinder in such a way that we get a displacement along or parallel to axis of cylinder. So that's how we can generate a screw dislocation using a Volterra cut. Now we'll be looking at how to mathematically derive a stress field around a screw dislocation using theory of elasticity for continuous media. So we take this as a continuum solid, and from this theory we try to find out what is the stress field around dislocation. Mind you, the core of the dislocation line where this theory of elasticity for continuum media will break down. So we can't find out a stress field around or very near to the core of the dislocation. Now let's mark our coordinate axis first. To do that, let's say this is x, y and z, where z is along a dislocation line or axis of the cylinder, and this is Burgess vector. So you have a Burgess vector here. So we have marked a Burgess vector which is parallel, will be parallel to this axis of cylinder or a dislocation line. So this is our dislocation line, and an assumption when we try to find out a stress field around a dislocation, we consider this dislocation line as to be infinite. So we have this infinite dislocation line, and let's mark this core. So I call this term as this region as a core of a dislocation marked by R0, and here this will be a length of a crystal, that is R, which is capital R. Now you can see that the linear elasticity is valid outside the dislocation line. So away from this dislocation line only, you have the linear elasticity will be valid, and thus we will be calculating stress field not exactly at the core or the near the dislocation line, but away from the dislocation line. So here you can see that the shear displacement in the xz plane along z direction. Let me mark that also. So we have a shear displacement on this plane. You can see that this plane which I am marking, so this complete plane, you have a shear displacement along z direction. So this is an xz plane, and you have a displacement on this plane along z direction. So to find out a stress field, what approach we should take is, let me write that down. So what we do is we find out displacements, and then we find out what are the strains there, and then we try to find out what are stresses. As we said that these are elastic stress fields will be there around dislocation. Elastic stress fields. So we can use elastic stress strain relationships here. So we use this relation. So when we get a displacement, we convert it into strains, and using elastic stress strain relations, we find out what are the stresses around it. So as you can understand this displacement, we try to find it in terms of tensors, and then we try to get a strain tensor also. Similarly, we get a stress tensor. So this will be an approach to find out stress field around dislocations. Figure it out what can be the displacements in tensors, then you find out what are strains, and then you find out stresses using elastic stress strain relations. So let's find out what are the displacements. So if you consider this screw dislocation here, that is u, that is displacement along x direction. So there is no displacement along x direction, so u will be 0. Similarly, there is no displacement along y direction, that is v equal to 0. But there is a displacement along z direction, that is we have sheared this along z direction, and we have some value of w, that is displacement along z direction, and which is a function of x and y. So this displacement along z direction, that is w, is a function of x and y, and it is not a function of z direction. Why? Because this dislocation line we are considering is an infinite, so every point here it resembles the point before, so that's why we can say that the w is function of x and y. Also, this displacement is varying along x and y plane, so we'll be looking at that and you will understand why this w is just a function of x and y. So this condition where w is independent of z, that is displacement along z direction is independent of z, and you don't have displacement along x and y direction, this condition is called as antiplane shears, and the strain corresponding to it is called as antiplane shear strain. So this displacement you can say is varying with respect to theta, which I have marked here. So you can say that let me write it down. So let's say you are at this plane, let's say this is an origin, you are at this plane, and when you move 2 pi, you will end up at a plane above it. So this is our Burgess vector, and this total degree is 2 pi. So when we move 2 pi, and this is our xy plane, let me mark that also. So this will be our xy plane. So if I move in xy plane by 2 pi, I will have shear strain developed along z direction, and thus this displacement is independent of even r also. R is nothing but, let me write it down. So this is a r, that is a radius of this cylinder. So if I write this as r, so this displacement when I traverse by 2 pi is also independent of r. When I consider a material to be isotropic, this displacement increases uniformly with theta. So that's what we tried to do. So here, let me write it down. So here we don't have any strain developed, or displacement is 0 here. And when I move by 2 pi, here at this location I have a displacement by a Burgess vector along z direction. So for an isotropic material, we can consider that this displacement increases uniformly with theta. Now you can find out this displacement, as I said. Let's say, let me write it down. Let me mark this here. So when I say this w, that is a displacement, will be equal to b theta upon 2 pi, where theta here, let me correct it. So theta is greater than equal to 0 or less than equal to 2 pi. So what we can say that when I traverse, like let's say this figure, so here I have a 0 displacement, and when I complete, or when I move along 2 pi r displacement, that is a circumference of the cylinder, there will be a displacement of b. So how we can write this? So let us understand this. So when I have 2 pi theta, I get b. So when I say theta, what can be the displacement? That is w. So W I can write it as B theta upon 2 pi. This is how we get this relation. And you can write this theta. Let me do that also. Let me write it down. So let's say we have defined these planes x and y, and this is our r and this is theta. So this point I can find it out with respect to theta as, so this theta I can write it as tan inverse of y upon x. So this is y and this is x. So we can write this w as b upon 2 pi. Let me correct this. So this will be b upon 2 pi tan inverse of y upon x. So I am writing this theta as tan inverse of y upon x. So when we write this displacement relation, and for anti-plane shear condition, you can say that the strain compatibility must be maintained. That is del square w equal to 0. So if you take this w as to be b upon 2 pi tan inverse of y upon x, you can say that del square w equal to 0. And what does compatibility means? So let's say I have an element which is, let's say I mark it as triangle, and when I deform it, it should deform something like this. Let's say shears, so all points are intact. It should not be like something like this where the joints are missing or there is no compatibility, or it should not cause, should not cause any overlap. So you should not have where the joints are broken or where the joints are overlapping each other. So these two conditions are doesn't satisfy strain compatibility. These are not strain compatibility conditions. Well, this is should satisfy strain compatibility. So to have this strain compatibility, this must be satisfied. What does that mean? So I can write it as del 2 w upon del x square plus del 2 w upon del y square equal to 0. So this condition must be satisfied, and this relation, that is this displacement along z direction, satisfies this strain compatibility condition. Now let's find out what are the strains, that is strain tensor in terms of a displacement tensors, and we have seen this relation that epsilon ij is equal to 1 upon 2 eij plus eji, and this is our strain tensor. And let's find out what are the components of this tensor. So you can write that epsilon xx is equal to du upon dx, and this is 0 because u is 0. Similarly, epsilon yy will be del v upon del y, and as v equal to 0, so this is equal to 0, and epsilon zz is equal to del w upon del z, and we have seen that this w is not a function of z, and thus it is equal to 0. Now epsilon xy is equal to epsilon yx. I can write it as 1 upon 2 del v upon del x plus del u upon del y. V with respect to x, displacement, that is v with respect to x, is 0. Similarly, u is 0 with respect to y. So this term, whole term, that is epsilon xy is equal to epsilon yx equal to 0. You have epsilon xz is equal to epsilon zx. I can write it as half del u upon del z plus del w upon del x, and I can say that this del u upon del z is not a function of z, or that u is not a function of z, and u itself is 0. So this term will be 0, and what you are left with is half del w upon del x. And this you can write it as, you take a derivative of this, and you can find it at, it comes out to be b upon 4 pi y upon x square plus y square. And in terms of theta, you can write this term as minus b upon 4 pi sine theta upon r. How can you do that? So you let me write it down. So you can write this 1 upon x square plus y square is equal to 1 upon r square, and from here you can find out what can be, or let's say I can write this term. Let me do that also for this term. So I can write this term as y upon r and 1 upon r. So this y upon r is nothing but sine theta. So it becomes sine theta upon r. So you can write this term, that is epsilon xz and epsilon zx, as minus b upon 4 pi y upon x square plus y square, or minus b upon 4 pi sine theta upon r. Similarly, you can find out what is epsilon yz and epsilon zy as half del v upon del z plus del w upon del y is equal to half, because v is not a function of z, as u is not a function of z. Similarly, v is not also a function of z, and this turns out to be 0. So you have half del w upon del y, and which comes out to be b upon 4 pi x upon x square plus y square. You have to differentiate this term using by y. And similarly, you can find out with respect to theta, it comes out to be b upon 4 pi cos theta upon r. And you can write this strain tensor where you have epsilon xx, epsilon yy, and epsilon zz to be 0. So this terms to be 0. And you have epsilon xy is equal to epsilon yx equal to 0. So these two terms are also 0. And what you are left with epsilon xz and epsilon yz. So you have these two terms, and this is the strain tensor which you get. We got the strain tensor. Now let's find out what are the stress field around the dislocation. So using elastic theory, you can find out sigma xx is equal to 2g epsilon xx plus lambda, which is Lam's constant, this we have seen, into epsilon xx plus epsilon yy plus epsilon zz. So these relations between stress and strains we can find out using an elastic theory, and these are the 6 stresses and the relation between the strains. We have got the strain tensor, and you can see that epsilon xx, epsilon yy, epsilon zz is equal to 0. So this sigma xx, sigma yy, and sigma zz will be 0. So we get sigma xx, sigma yy, and sigma zz equal to 0. Similarly, you can see that tau xy and tau yx turns out to be 0. You have left with tau xz, that is this term, and you can find out using 2g epsilon xz, where g is shear modulus, and you get tau xz to be minus gb upon 2 pi y upon x square plus y square. And in terms of theta, you can write it as minus gb upon 2 pi sine theta upon r. Similarly, tau yz is equal to tau zy, and it is given as 2g epsilon yz, and you get this term. You just replace epsilon yz is this term, which comes out to be gb upon 2 pi x upon x square plus y square, and in terms of theta, it is, you can write it as gb upon 2 pi cos theta upon r. Now here you can find out a stress tensor, and here you put values of tau xz and tau yz, and you don't have any normal stresses, and you don't have tau xy or tau yx. So here from this strain tensor or stress tensor, you can say that there are only shear components are present and there are no normal components. So you can see that here I have just only a shear components and there are no normal components. So thus the stress field around a screw dislocation has only shear component, and thus no normal components over here. What does that indicate? That it doesn't have any hydrostatic stress state, while it just have deviatory. So you just have deviatory stress state around a screw dislocation, and thus it doesn't have any hydrostatic, and we'll see the implications of this when the screw dislocation interacts with another screw dislocation, other dislocation, or other defects in a crystal. So with this, I will stop here.